Hello friends, welcome to our YouTube channel. In this series of basic process engineering calculations. In this session number 16, our main focus is to how to calculate the cooling tower capacity, its blowdown rate, evaporation rate, and its basic other things like what is meant by range and approach. Okay, so first to perform the calculation we need to assume something. As we have performed the energy balance calculation, I just consider that we have performed the energy balance calculation. So we have how much amount of heat uh, is available with us, and to remove that much amount of heat, what actually cooling water circulation flow rate required. Okay, so here I consider cooling water circulation flow rate. Okay, this is our main assumption. So here I assume that 520 meter cube to perform the calculation. Okay, so it's the main cooling flow rate, cooling water flow rate required. So here I have mentioned hot water temperature. Okay, it is a temperature of hot water which is returned from the plant. So I'll just assume that temperature may vary based on the heat uh, duty available in the plant. Then cool water temperature, which is the cooling water temperature, that is the how much amount of or what is the actual temperature of cooled water after passing through the cooling tower seals. Okay, so we need wet bulb temperature to perform the its effectiveness and related calculation. Temperature, that wet bulb temperature may vary area to area. If you perform these calculations for the cooling tower in the areas like the desert or the hot area where the humidity is on lower side, you will get the wet bulb temperature different. If you check this for the humid area like seashore areas or the uh, industries those are located near to the sea face or coastal areas. Okay, so first we will check range. What is mean by the range of cooling tower? This is the common question asked sometimes in an interview of the freshers or 1 2 3 4 plus years of experience to the process engineers. So you should know that the what is mean by the range of cooling water or cooling tower. So basically, range is the difference between the hot water temperature minus the cool water temperature. What is the actual difference in the cooling towers? Then another parameter is the approach of cooling. What is the approach of cooling tower? Sometimes this is also asked during the interviews or in examinations also. Yes. So approach is the basically difference between the cool water temperature minus the wet bulb temperature. Okay, this gives us the idea about the effectiveness of the cooling tower. Okay, then how to check the effectiveness of the cooling tower? Okay, effectiveness of cooling tower. Basically, effectiveness is equals to range divided by range plus approach. Okay, or you can multiply simply into 100 so that you will get the effectiveness in terms of percentage. Okay, so here we will calculate the effectiveness of this cooling tower which we have considered. for the reference calculations, this is a range divided by range plus approach, okay, and into 100, so that you will get the efficiency or the effectiveness of cooling tower in terms of percentage. Okay, so hope you got that much clarity till now. Okay, so now we can calculate the other uh, calculations. Okay, so basically effectiveness is the depends on the majorly approach. Okay, so here we have performed the first calculation of range, second is of approach, then the third calculation required for us is the effectiveness, then we can perform the calculations further. Okay, so as we have to calculate the another factor is the cycle of concentration. Okay, as you have listened, like what is mean by COC, is the cycle of concentration. Okay, so COC, how to calculate COC is equal to the TDS in the circulating water divided by the TDS of makeup water. Okay, TDS mean by the total dissolved solids. Okay, so to calculate that we need to input some values of the TDS in the makeup water. It is the standard or the specification of the inlet water from the MIDC or GADC or borewell that we used in the cooling water. Okay, TDS in the circulating water. Okay, and as the water used in the cooling network through the piping and the atmospheric some dust via mist as a mist or the air that gets dissolved in the water or suspended, so the TDS level will increase. So basically 500 to 600 ppm level is in the fresh makeup water, and we need to change that after 100 or 1500 or the 1800, so we need to make up that. Okay, so here I have mentioned that the TDS level, so we can get the value of COC. Okay, so COC is the cycle of concentration for this particular cooling tower. We can calculate with the simply this the TDS in the circulating water by this is the number of COC, so that gives maybe it's in between range of 3 to 4. So now we got the COC value, that value required to calculate the evaporation losses. Then second, as you know, there are evaporation losses during the cooling tower operation. If you have checked the cooling tower working the fan, above the fan you will observe some vapors flowing. That is the actually evaporation loss. So how to calculate this evaporation loss is equal to the basically we have standard formula for this H5 into the circulation flow rate into the range which we have already calculated. Okay, so here to calculate that we have to put all the values which we have available. We have considered 520 meter cube of flow rate of the cooling water circulation. So into that we need to put the our range value, what is the available with us, as here we have calculated the range value. So we got the 2.21 something meter cube per hour of evaporation loss. So then we have to calculate the blow down frequency or blow down losses. As we are blow down after certain duration, that means that is actually calculated as a loss. Okay, so blow down loss is calculated simply. Blow down loss is equals to the evaporation loss divided by COC. Now you got the idea about what is the COC. It's the cycle of concentration which we have already calculated here. Okay, so simply divide that, the evaporation loss divided by COC minus 1. So it's 1.10 meter cube per hour is the blow down rate, or the, okay, which we needs to blow down after reaching the TDS level of 1800 ppm. Okay, so then we need to calculate the drift losses. Okay, how to calculate the drift losses? Drift losses is the, based on the thumb rule, you can calculate 0.001 into the circulation water flow rate. Okay, circulation water flow rate. Okay, so here 0.001 into, what is the circulation flow rate which we have assumed here is the 520 meter cube. That is mean by the, this is the drift losses. Till now we have calculated the evaporation loss, blowdown loss, and the drift losses. Okay, so there is the another factor or another loss, type of loss, which we generally didn't gone through during our academic. Okay, backwash loss. Okay, backwash loss is basically 3% of the side stream flow rate. Okay, if you look in any of the particular cooling tower, there is one of the side stream that passes through one of the filter media to capture the suspended particles, to remove the dust or debris or whatever it may be, comes through the cooling tower or cooling water from the plant circulation network. Okay, so here I just assume side stream filter flow rate. Okay, so filter flow rate which we have designed, that is for the 25 meter cube per hour. Okay, 25 meter cube per hour flow rate is the circulating through the what we call the backwash filter. Okay, backwash loss. So here backwash loss is, I already told you that, into 3%. So 0.75 meter cube per hour is are the backwash loss. Okay, so till now we have calculated the evaporation loss, blowdown loss, drift loss, and the backwash loss. So now you have to decide the, what is the actual quantity or the makeup water required. Okay, so the makeup water required, so makeup water required is a, oh, basically makeup water required is basically sum of evaporation loss plus blowdown loss, then the drift loss and the backwash loss. Some industries don't have that backwash loss uh, in the cooling water calculation, so here I just have calculated that backwash loss considering the our actual operation. So here the makeup water is equal to backwash loss plus the drift losses plus blowdown loss and then the makeup or evaporation loss. So that much amount of cooling water required as the makeup. Okay, now you got the, I hope you got the idea about the how to calculate the makeup water quantity required. Okay, so simply I just highlight first here what are the actual calculations we have performed, so you will get the idea about the what we have calculated and which for with the reference of which formula. These are our basic calculations, then cycle of concentration, okay, and range and effectiveness. Just highlight to each calculated part, so you will get the idea about which calculations we have performed and what data we need to perform these calculations. Okay, so till now you got the idea about the calculations. Then also we need to decide the cooling tower capacity. Okay, or the sum first we will decide the cooling. Sorry, I just need to mention the cooling tower capacity. Okay, what how much quantity or how much the cooling tower uh, TR requires. Okay, so that TR is vary based on the what we call the temperature difference assumption. Some cooling tower manufacturers consider 10 as a range, some consider 8 as a range. Okay, so here we will consider simply 5 degree as a range. So based on that we have to cooling tower capacity. Okay, capacity is equals to what is the, it's simply a mcp delta t, so I just simply write as a circulation rate, m is our mass, okay, into range into the specific heat of water, and that needs to converted into the TR. To convert that into TR, we just needs to convert that simply by dividing 3024. Okay, so now we have to calculate the capacity of cooling tower. So as I have stated here, we need to consider the flow 520, it's in meter cube per hour, so I have converted that into the mass flow rate, okay, into the range of cooling towers into the specific heat. I just simply put it here, so and total divided by okay, so it this value we get 1, okay, 1 kilocalorie per kg Kelvin. It's the specific heat of cooling water. Okay, so the value we got in the kilocalorie. Okay, so I just kilocalorie per hour. So we have to convert that kilocalorie. As I stated here, we need to divide that into 3024, so we'll get that value into TR. Okay, that much of the cooling tower capacity required. Cooling tower capacity. Okay, it's the required. So here we need to consider diversity factor of 10%. So we'll get, and the future expansion of 10%. So you, if you are doing any modification in the existing system, so you will need not to change the cooling tower or the look for the new cooling tower for small changes during the process improvement. So that's why I have considered that 10% of future expansion. You can consider based on the whatever the uh, actual requirements of your organization, or whatever you called it specifically. It's the calculated cooling tower capacity is the 1000 TR, 1040 TR. Okay, so I'll just highlight it. Now you got the idea about the basic calculation, backwash loss, blowdown loss, makeup water, and all these things, cooling water or cooling tower capacity. Vendor can suggest based on their standard models which fitting to your requirements, but we need to calculate that much of the basic calculations prior to sending inquiry to the vendor. Then I got sometimes you got confusion about, yes, it's okay. We got cooling tower pump capacity or the cooling tower capacity, but what is the actual the sump capacity required? Cooling tower basin. Okay, so sometimes you got the question about how to calculate the cooling tower basin volume. Sometimes vendor provides in FRP, but most of the industries prefer to have the RCC sump, uh, so accommodate their requirements. Okay, so basically sump volume calculated based on the experiences, and I just simply put one reference formula so that you will get the idea about. So we need how much amount of residence or retention time in minute into the flow rate of the pump or the circulation flow rate. Some simply we can call it as the circulation flow rate, divided by 60. So you'll get the basic idea about the how to what much how much amount of the some volume required. Okay, retention time basically you can consider as 5 minutes. Sometimes some industry prefer to have the 10 minutes prior to because that some volume requires in case of power failure, so or the breakdown in cooling tower fan, so you will get at least some buffer time to cool or to remove the heat. Okay, so I just here consider the retention time of 5 minutes. You can consider based on your requirement. So simply we can calculate the retention time into the circulation flow rate. Okay, circulation flow rate divided by 60. So that much amount of basin volume required. Okay, this is the basic calculation related to the cooling towers. Hope you got the idea about how to perform these calculations, and that I hope that is the simple or clear enough so you can perform this calculation at your own using the simple Excel file. So still, if you have any doubt or any queries or any suggestions, you can drop me a message in a comment section. We'll get back to you. So thank you for now. Bye bye.